hyperelliptic, and so we had an involution here, translation along the fibers, and here the hyperelliptic involution, which has a certain number of fixed points here. And so this is of genus G with G greater than or equal to 2. And so here we had here an unramified or étale 2-to-1 map to some X here, which fibered, also with the generic fiber being E, and so over P1, which was just CG divided by the hyperelliptic involution. And so this means that here, if we took this first, this is the Itaka-Moishezan fibration here in this case, and so if we try to apply this decomposition theorem that we had by taking successively rational quotients and Itaka fibrations, so we see that in this X we don't see anything of general type which is happening, because here we have elliptic curves of fibers, and here we have P1 just, which is certainly not of a general type. But as we might have seen here yesterday, on the other hand, by taking just this étale cover, we see that we have here something which is of general type, which happens. So this means that here, if we compute the fundamental group or different invariants, we see this is very easy, in fact, that you have really some part of general type in this, that you don't see by taking these successive quotients. So the way to see what is this the general type part is by looking at this. This comes, of course, from this CG, but if we ignore the construction, we just want to see here on this side, without ignoring this, that we have something of a general type, and as we have seen before, the natural object was this delta, where delta here, this is a certain divisor, which is obtained by looking at the multiple fibers. And so the multiple fibers, they give some kind of ramification, if you want, and so we have this. And seen in a different way, if we take let me call this map here, this is F. So F star of KP1 here, because this is certainly something on X. If we look at the kappa of X and F star of KP1, so we certainly get minus infinity, which is just kappa of P1 here. So we don't see anything just by taking the inverse image of this. But if we take the saturation of this F star in KP1 here, so this is a line bundle which is a little bit larger, then what we shall get, that this is +1. And so we get something, and this is no longer, but this will be the kappa of P1, and here, let me tell this delta. Because this is a curve with certain points and multiplicities which give general type. And so this is the thing that we are going now to extend. And let me remember you, because here in some places we have some double fibers here, which appear on this projection, so we have double fibers. So this means that when we take F star of KP1, this F star of KP1, this will actually vanish along the fibers. And taking the saturation, this corresponds exactly to adding certain poles. But these are not poles because precisely when we lift this, we have a certain vanishing, and so this means that we can allow certain poles, and so take the inverse image. So the saturation, so if you see this orbifold structure here, this corresponds also to saturation, and this is what I will explain. And now, so the first part will be about some, which I call Bogomolov sheaves. Bogomolov sheaves. And so the theorem is this in general. This is due to Bogomolov. This is an older result of Bogomolov, 1978, I believe. And so if we have X, which has a dimension n, projective, smooth, for example, and assume that we have a certain L, which is in omega p x for some p positive, say. And so assume that this is rank 1. And a coherent, so if you prefer, you can assume that this is a line bundle. Then we have the following inequality, which is kappa of xl. Here, this is less than or equal to p. And let me insist that the p is the same p as here. And so this is less than n. So, in other words, when you take a subsheaf in some omega p here, the Kodaira dimension of this line bundle here can't exceed p. Okay? So if you take p is equal to n, the only possibility that you have is this is the canonical bundle. And so you get n, of course. But in general, this will be smaller than n. So, and for example, if p is 1, for example, then the bound is very strong because this is just 1. You can't have something which is very positive if this is inside of this. Then we have first 1 and 2. If kappa of xl, this is equal to p. So if this is the maximum, if the maximum is achieved, then there exists a fibration f from x to some z, which is of dimension p. This is rational in general, but not so that important. So the p here, this means that this is of dimension p, such that L is equal to f star of kz generically on x. So this means at the generic point we have this. So, but this doesn't mean quotient. This doesn't mean that Z is of a general type. Let me abbreviate general type by this. General type means that kappa of Z is dimension of Z. This doesn't mean that f star of kz is of dimension p. Actually, what is true, that this, if we take the saturation, then this will have a dimension p. So, but we have all the point is to go here from this f star kz to the saturation. And so the picture is exactly similar. And so this gives you an example in which you have something, an f, if you take the saturation of this, so this is L. If we take this L here, saturated, then this has this is a Bogomolov sheaf. In this case, let me call it, we call it then L is a Bogomolov sheaf. Let me give this name.
Vibration?
Hmm?
Is it vibration?
It's a vibration, yes, with connected fibers. Yes, connected fibers. A priori, this is only rational, but the thing is completely invariant and well-defined. So we have this. And now I will use this in order just to give a definition. The first definition, but we shall see later that we need geometric interpretation. So the important thing, what we shall do later, is to interpret, I will say this, definition, X is special if there is no Bogomolov sheaf in omega px, and this for any p positive. So this is the definition. Let me notice one first thing is that X special, certainly. This implies that X is very weakly special. Where very weakly special means that you have no vibration on some ZP of general type and positive dimension. So this is certainly, this is obvious because if you have such a vibration, then you just have to lift the canonical bundle of Kz. And so this gives you a subsheaf, a Bogomolov sheaf inside of omega p. So no Bogomolov sheaf implies no vibration on something of general type. But as we shall see later, this is much stronger than being very weakly positive.
So this is birational state, right?
This is birational.
For example, a priori it can be rational map, right?
Yes, rational maps.
Then you have to go up.
Yes. So this is a completely birational, and I will state something which is not obvious. So being birational, this is easy. Property of being special, this is birational, as you said. But this is also étal, plus étal. And so this is a non-obvious fact. I will speak later on this. This is étal, meaning the following, that if you have an X which is special, all of its finite étal covers are also special. So this means that we avoid this kind of a problem. So this will not happen. If you have something which is special, you will not have this kind of phenomenon. So this is also an important thing. And so what did I want to say? And now we will interpret precisely. Now the objective, the main step here is to interpret geometrically the difference. The difference between kappa of X and then f star of Kz saturated minus kappa of X and f star Kz. So do you see, we have two sheaves here. The first one is the line bundle f star of Kz, and a second one which is larger, which is its saturation. And now we will give an interpretation of this difference. Of course, this difference is certainly positive, because this one is larger than this one. Okay, and so now this, unfortunately, here, and the reason for interpreting this, we will be in this situation. So this means that we have to equip the base of a vibration, of any vibration, with a certain structure which comes from the multiple fibers, and this is precisely orbifold structure, orbifold pair. And so I have to introduce the orbifold pairs. I will just give a very short interpretation. An orbifold pair, this will be a pair XD, where X, you can make it more general, but if this is projective smooth, say. And D, this is a divisor which has the following form, AY, AJ, DJ, so this is a finite sum, in which this is exactly the same as for log pairs, but I prefer the term where AJ, say, belong to 0 and 1, intersected with Q. Intersected with Q. So we take such a combination, and here, instead of this, to make things a little bit more geometric, we have to write this. Maybe I write it as Cj. This coefficient. Cj, this is the coefficient, and this is equivalent to something which is the multiplicity. And the multiplicity, this Cj, we can write it in a unique way in the form 1 minus Mj, where Mj are certain rational numbers. And Mj, multiplicity, this is Mj. And so Mj, now this is certainly strictly greater than 1. 1 corresponds to 0 here. If you have Mj which is equal to 1, so you get coefficient 0. And if Mj is strictly larger than 1, then you have something which is less less than 1 and still positive. And if you want to have Cj which is E1, you need to have this 1 over Mj is equal to 0, so this means that Mj is infinite. Excuse me, is plus infinite. So this multiplicity now, this corresponds to something, to a rational number which lies between 1 and plus infinity. And plus infinity, this corresponds to coefficient 1 here. And so let me give you a very short interpretation of what it means. For example, assume that this d is 0, and you just get x, nothing else. Now, if all the coefficients are equal to 1 here, all multiplicities are equal to infinity, this corresponds to the projective case of purely logarithmic case. This is essentially the complement of d. This is just x minus d. And now in the intermediate situation in which mj, for example, are integers, if the mj are integers, you can imagine that this pair, this is something like a virtual ramified cover of x, which ramifies at order mj over each of the dj's. So this is the interpretation, and this is exactly what you have here in this side. Here you have a global cover which ramifies exactly, but in general, and especially in higher dimensions, you don't have this cover. And so you have to work rather with these objects directly. And so there are a special case. I say that xd is smooth if this is, say, log smooth. So this means that x is projective, let me assume to be smooth. And so this is smooth if the support is d is SNC. So this is the roundup of d is SNC. So this means that you replace the coefficients by 1. So this is the union of all dj's, and so this is SNC. And we say that this is integral if the mj's, the multiplicity, they belong to z union, z positive union plus infinity. So if all coefficients are either integral or plus infinity. So this is an integral. So now, of course, because of this example, now we shall see associated to this kind of objects, you can make much geometry with this. In particular, you can define a cotangent bundle and jet differentials and many things. On the, I would say, yes, a differential geometric side, but you can also introduce other invariants. For example, if in the integral case, if the multiplicities are integral, so in this case you can introduce also a pi1, fundamental group, and also the notion of integral points or rational points. So I will not, this will be rather the objective of the next talk to speak a little bit about this, but here you have a lot of geometry. And I will only introduce the simplest thing, which is just the canonical bundle of x, k of x d. By definition, this will be kx plus d, so this is very standard, and of course kappa of x, and let me call d, here this will be by definition, kappa of x and then kx plus d. And we say that xd is of general type if kappa of x d is equal to the dimension of x. So we have this. So this is the very simple thing. And now we are interested in trying to split any x in parts which have Kodaira dimension 0 or essentially minus infinity or general type. And so, yes, so what is the basic example of such xd? This is for following. This is the base orbifold. I will maybe write it correctly. Orbital base. Yes, British have the habit to intervene about everything, and so this is the orbital base of the vibration. That's all. The object is this. Now we have X, which goes onto Z, and I assume that the fibers are connected, for example. So, and this is onto, and so I will define first for any F in Z. This is an irreducible divisor. This is an irreducible divisor. I will define a multiplicity. Mf of F, this will be the following thing. This will be the following thing. Take F star of F. I assume just to simplify, but this is not needed. That Z is a smooth too. F star of F will be just the sum of some Tk, Ek, plus a rest. And so, what are the Eks? So this is just here where Eks are the irreducible components of F minus 1 of F, such that we have F of Ek is equal to F for any K. And the rest, this is the F exceptional part. Minus 1 of F. So, if you take F minus 1 of F, this is a divisor. This is a divisor which is supported on two kind of things, of components. You have first the components which are mapped surjectively onto F, and so on the other hand, you have the components which are mapped in codimension 2 or more inside of E, of F. Okay, so you have this. So I ignore this. There will be a price to pay. So we ignore this for the time being. And so now we can define here Mf of F. This is the infimum of the Tk for K belonging to K. Okay. So let me make a remark that you have a classical. So what is the meaning of this? What is the meaning of this? If you are in dimension 1, this is very easy, because if Z is dimension 1, for example, then the situation is very easy. You take a point and you have a certain number of components. You have no rest in this case. So you have a certain number of components. These components here, you take the inverse image of a point. This is just the inverse image of a point. So you have this, and so you take just the minimum of the multiplicities. But if you have already seen things in a surface classification, you see that usually the people, they don't consider the infimum, but the classical multiplicity, which is just the M star of F, which will be just the GCD of the TKs. This will be the GCD. This is very different, because assume, for example, that we have just two components with a multiplicity 3 and a multiplicity 2. If you take this M star, you get GCD, nothing. This is 1. So you have no multiplicity. But if you take this, now you will have 2, multiplicity 2. So apparently this means Not a big difference, but the difference is huge, actually. And so this is, I think this is the correct definition, at least for the classification program. So we have this. What I wanted to say, yes, and let me give you an example which explains a little bit why the people were not so, till now, so much interested in this, in the difference between the two notions. First, the first thing, if xz, if xz, if this is rationally connected for the generic fiber, so this is the generic fiber, and if you assume that this, then we have always mf of f is always 1, so you have no multiplicity. So this is a theorem of Graber-Harris star. This is important, very important theorem, non-trivial here. So you have this problem, and the second thing, if xz is an abelian variety, for example, an elliptic curve. An elliptic curve, then we have also mf of f, this is equal to mf star of f. So you have no difference between classical multiplicities and these, the actual multiplicities. So you have no difference in this case. And for example, and the people have considered this kind of orbital structures in the case where X is a surface, an elliptic surface mapping to a curve. And so they didn't have to make the difference between the things, and they don't have seen that there is, how to say, an issue there. They didn't need to notice this, actually. And now we have this, what did I want to say about this? Yes, I didn't define the orbital base. And now the orbital base of F, this is just the pair. This will be Z, and let me call it dz, df, with df. By definition, this is the sum over all f inside of z of 1 minus 1 over mf of f here dot f. And so this is a divisor on z. This is a Q divisor on Z. Actually, this is an integral orbital pair in this situation. So you have this definition, and let me notice that here the sum is finite. The finite sum, because in order to have a certain multiplicity, you need to be inside of a discriminant locus, so where the map is not smooth. So you have only a finite number of such things, and so this is really an orbital pair in this situation, and even an integral one. I would like to make a further small remark, and I will not give an exact definition, although it's not very complicated. But even if we have a certain xd here, if we have already an orbital structure on X, we can define another, one can define naturally. There is also a definition of dfd here. If we have some xd, we have a definition. The definition is not very different. You just have to multiply this tk by m inside of d of ek. You just multiply this. The reason for this is just if you make a composition of vibrations, then you have to compute the orbital base of the composition of two vibrations, and so you can compute it in terms of this intermediate thing. But I will not go. But this is important to have this in general. Yeah, I think I have everything. Now, there is a trouble here, birational equivalence of vibrations. Birational equivalence of vibration, this is the following. If we have assumed that I have an X which goes to an F, to a Z here, and that I make a birational change on both sides here. So I have V and I have U here and I have some F prime. In general, you may be interested to know how things change. And so there is in some sense a relatively easy thing, which is that F star of D F prime, so we have D F prime here. We take the direct image here, and this is DF, so very good. On the other hand, the only problem is that on the exceptional divisor, you may have troubles because the multiplicity on the exceptional divisors here may be too small. And so it means it will in general happen that kappa of Z prime and then K Z prime plus D F prime might be less than or equal in general than kappa of Z and then KZ plus DF in general. This implies the following. So you have this, and in general you may have strict inequality. This is possible. This is possible, and this will happen. And so this is a very big problem because we want to have really a good notion of this. And I will not go, but there exist always neat models of F such that no problem. No problem. So this means that these neat models, they will achieve immediately the possible minimum. The minimum here, it has a meaning, and they will achieve the minimum. And so I will always assume here in the following, in order to avoid the technicalities, but just to keep ideas, that I'm working on neat models of things. Because once you have these neat models, I will say maybe in 2 words what it means. You have first to flatten your F, you flatten F, you make a desingularization, and then you make some further blow-ups in order to have an orbital base here of df prime, such that z prime, df prime, you want also this to be smooth. And so this is possible by making some suitable modifications on z and on x prime. I will not describe the things. This is just to keep the idea. So we are always assuming that we have neat models. And so in this sense, I will always define kappa of z and kz plus df. Let me call just kappa of f here. So for neat, this is on a neat model. In a neat model, and I would like also to mention that this is well-defined, even well-defined, even if, if we have f, this is something which is just a rational vibration of something, so you can define it. So you have to blow up X, you make it regular, and then you take a neat model, and so, and this will be what I mean. And now, when we have this, now we have the next theorem. The theorem is the following. Let for any f from X to Z, let us say that this is neat. Neat. So we have a certain orbital base, Z and df, which is here. And now we have also something which is f star of kz. And let me I take the saturation. This is inside of omega p of x if p is the dimension of z. So I have this thing. And let me call this will be LF here, or maybe LF. LF, then the theorem, we have the following, kappa of x and then LF, this is equal to kappa of y and then kappa the y, this, and kz plus df. And so if you want, here we have the explanation, the geometric interpretation of what may happen in the theorem of Bogomolov, which has been erased here. This explains essentially where the difference comes from. So we have this, and so let me interpret this. Notice a remark. So this means also the following, that kappa of x and f star kz saturated minus kappa of x and f star of kz. This is very simple. This is essentially the meaning of this. This is the same thing as kappa of z and kz plus df minus kappa of z. So do you see? And so this exactly tells you that the increase is exactly given by this orbifold base structure. So this is exactly what happened in the former result. And so what I would like to mention also, that this is true with the non-classical multiplicities. With the multiplicities, the infimum multiplicities, and certainly not with the classical multiplicities. Classical multiplicities are too weak in order to get this kind of equality. Not true. Not true for classical. For classical MF of F. And so this is the main reason why I introduce this infimum multiplicity. And this infimum multiplicity gives a lot of trouble in arithmetics, for example. This is they lead really to completely new phenomena. For example, and I will speak a little bit on the next talk, you have for curves, you have the model conjecture, which has been solved by Faltings, but you have now for curves also an orbifold model conjecture, which I have formulated, which is open, which is a consequence of ABC, but which is open. ABC is open as far as I know, presently. So we have this separation. So we have this. Now let me with CNM orbifold conjecture. And I give just the simplest version. This is the following. Let f x to z, and I assume it to be neat. Neat, then kappa of x is greater than or equal than kappa of x z plus kappa of z, and here I have kz plus df here. So for this conjecture, this was formulated with just kz here, and not kz plus df by Itaka a long time ago. This is still an open in general. I would like to mention that there is also orbifold version. If we have a d here, this will be larger than kz, and here I take d restricted to kz, which is log smooth, plus kappa of z, and here I have to put this stronger thing. This is possible to get. This is a general version. If you want, let us forget this. But this is very useful to have this, for example. But because in case X is, for example, a projective space or something, a Fano manifold, for example, you can add some things. In general, if you have just this is minus infinity, and so you have minus infinity here, and so you have nothing. But here, if you add this thing, then you may have something which is of a positive Kodaira dimension here, and so you will have statement. So the extension is this is very useful. Although a priori, in the known case, the proof is not very different, but the range of application is much larger if you have this. So I just take this thing. And so this is open. But now this is a theorem, and which is essentially, this is the proof is a variation of Fiveg from, which tells that this is true if kappa of z and then kz plus df is equal to dimension of z. So in other words, if the orbital base is of a general type, then this is true. So Fiveg showed the case where you have this, no df, for example, but the stronger version can be obtained by a variation of his proof. So you have essentially this result. And let me give just an important application example. Corollary is this. So you have, of course, more general versions with where you have these, but I don't go into this. Corollary, if kappa of x is greater than or equal to 0, then we have kappa of z and kz plus df is certainly strictly less than d for any f. So you never have an orbital base of general type if you have kappa of x, which is which is equal to 0. Sorry. Which is equal to 0. You don't have. Why is this? This is for a very simple reason. For any f, and of course with dimension of z, I'm assuming that dimension of z is positive. Because look at this, here you should get 0 here at this place. Now, if you have a divisor here, a section of some, this will induce also a section on the general fiber, so this will be positive or 0. And on the other hand, if this is strictly positive, you get a contradiction. So this means that you get this thing. In other words, what does it mean? Kappa is 0, this implies that x is special. Yes, because I should have mentioned it at this place. Now we have, notice, we have two definitions for x being special. X special, this is equivalent to first the thing that we have kappa of x, L is strictly less than P for any L in omega P, rank 1, and P positive. Now this is also equivalent to kappa of Z and KZ plus DF is strictly less than dimension of Z for any F from X to Z, say, need. For any F and with Z, P and P positive. So we have two definitions for X being special. The first one is just by looking at these sheaves of differentials, and the second one is geometric by looking at the orbital base of fibrations. So you have this result. And so we have this property. And now I will go to the special manifolds. Special manifolds, I will give some examples. And so the first thing, if n is 1. So if we have curves, so x1 is special, this is equivalent to g is 0 or 1. So this is elliptic or rational. And this is for a very simple reason, because the only omega p you can choose is p is equal to 1, and then the only thing is kx. And so kx, either it is general type, so or not. And so you have this. So we have immediate generalization. X is rationally connected. This implies special. And this is very obvious because we have a much stronger thing. In this case, that the tensorize of omega 1 of x is 0 for any n positive. So this is a very obvious that you have such thing. Now the second thing, so this generalized g is 0. Now the g is 1, this is generalized by kappa of x is 0. This implies that this is special, and this is the theorem, this is the corollary, which is here. So you have this generalization. Now we are, this is 3. Now 4, maybe I will take n is equal to 2, so the case of surfaces. And so I have the following characterization, that x is special, but surfaces, this is a small dimension still, and so you have some special phenomena which happen. X is special if and only if you certainly need kappa of x is less than 2, x2, kappa of x, and you have pi 1 of x is almost abelian. I will explain a little bit later where this does come from. So this means that we have a very simple characterization, and in particular, surface being special, this is stable by deformation and specialization. Just because this is given by the kappa, which is invariant by deformation, we know this now, and pi 1 of x, which is just a topological invariant. And so you have this almost abelian. This means that it has a subgroup of finite index which is abelian, or equivalently you have a finite étale cover which has an abelian fundamental group. We will see a little bit later a description, but let us get this. One has to pay attention now to one thing. K-free surfaces are, of course, special. Yes, what I should say, yes, kappa of x is 0. So, for example, you take abelian varieties. This is certainly true. This is very obvious because omega 1 is trivial. Omega 1, the cotangent bundle is trivial. So this is very easy. Another case which is easier also, this is when C1 is equal to 0, because in this case you have the differential geometric methods, and or in the projective case you have a Miyaoka theorem which permits also to give a different proof. But here for kappa of x is 0, we get, in fact, also in the case C1 is 0, you have a much stronger conclusion. Namely, not only is for this L, not only are these LF never of general type, but actually their codirectional dimension is always less than or equal to 0, which is much stronger. And we expect this in general, but for kappa of x is 0, but this is not. So this is very far from being the optimal thing which is expected. For we have 4, yes, 5. Remark, caution. One might expect that special manifolds have a codirectional dimension which is minus infinity or 0. This is very wrong. Caution, for any n, say positive, and for any kappa, which belongs to minus infinity, 0, 1, and n minus 1. So we avoid, of course, carefully n. There exists xn, dimension n, such that kappa of xn is kappa and xn is special. So in other terms, product, let me think. This will not work with product. You need to have variation to produce this. Product will not work. Huh?
Surface, ruled surface.
Ruled surface. Ah, yes, but the interesting thing is to have a large codierad dimension. This is interesting. I want to avoid minus infinity, which is very easy. You have Pn. But let me example with n, any n, and with n minus 1. Maybe n, let me take it greater than or equal to 2. And so you just take x inside of P2 cross Pn minus 1. This is a smooth hypersurface of by degree 3 and d. And d we see, which is sufficiently large, I think n plus 2 should be sufficient. Do you see, if you take a hypersurface, here in this smooth hypersurface, of course, so you will have a codierad dimension, which will be n minus 1 coming from this, and here you have a kind of Weierstrass model on this here, so on the elliptic fibration, and it's possible to show that this is special because you have no orbital base in this situation. So this is a point. Yes, and a different example, 6 maybe. If we have a Cn, this is a meromorphic map to Xn and not degenerate. And I don't assume that this is an algebraic map, but just really a completely transcendental map. Then this means then this is special. Then X is special. So this is a very different object and kind of criterion which can be made more general. So this means here not degenerate. This means that at a certain point this is regular, of course, and then that the Jacobian does not vanish. So this is just the meaning. But you may have a very transcendental map here, and this implies already special. This is a version of a Kobayashi-Yoshai from an orbifold version of a Kobayashi-Yoshai from. So these are the special manifolds. Yes, for the case of n is 2, let me explain how one comes from this. So assume that we have X, which may be S. This is a smooth projective surface. And so if kappa is minus infinity, as we know, S is essentially P1 cross C. And C with a certain genus, so you have three possibilities essentially. Either the genus is 0 or 1, and so this is a special, or this is of a hyperbolic, and then certainly this is not very weakly special, and so it's not special. But this corresponds exactly to the case that the fundamental group is not almost abelian. Now, kappa is 0, then S prime or S tilde, so this is some. This is either a Khafre or abelian, and so in this case, this is not too difficult. We know that all of these are special, and that the fundamental group certainly is almost abelian. Now, the interesting case, and this is the last case, kappa is 2. Kappa is 2, so this is certainly excluded. But in this case, we have an elliptic fibration F on some, this is S, elliptic fibration on some curve C, and this is elliptic. And now there is an important thing that you can essentially, I forget some special cases, which are easy to deal with. You can take a finite étale cover here, which eliminates the multiple fibers. So this means that in this case, you have no longer orbifold base. So I assume that I'm not in the orbifold base case. So there is no orbifold structure. So this is a very special feature in dimension 2, that the only fibrations that you may have are onto curves, and on curves you have very special properties for orbifolds. You can remove the orbifold, but this is no longer true when the base here is of dimension 2 or more. So this is completely wrong from dimension 3 on. And so, but I use here this property, and so you get then pi 1 of C, and here we have pi 1 of the fiber. So you have an exact sequence of group here. So if this curve is hyperbolic, certainly this is not special. Now, what you have to show, if this is, and this is very clear also, that you have no multiple fibers here. So if the curve is elliptic or rational, then this has to be a special manifold. So this is very easy because you don't have orbifold fibrations with orbifold base. So this is very easy. What I have used is that being special is also invariant under finite covers, and so we have this property. What did I? Yes, and so you have to just to check that in this case the fundamental group is almost abelian. So if C is P1, this is certainly clear that this, because this will be a quotient of pi 1 of f. If C is an elliptic curve, so you have an extension of this, and then you have to use Hodge theoretic properties in order to show that this is still an almost abelian group. This is not. This is very classical, but not entirely trivial in this case. So this is how one can get the equivalence between these two properties. In dimension 3, the situation is very different. Dimension 3, there exists simply connected pi 1 of x3 is 1 with x3 which map to a certain surface S2 with kappa of S2. This is less than or equal to 1. You can choose whatever you want. This is an elliptic fibration, but where the orbifold base is of general type. Let me briefly mention this. From dimension 3 on, the situation is much more complicated. It's much more complicated, and this is not easy to construct this kind of example with simply connected, because then this shows that here you can't make étal covers in order to get something which goes to something of a general type. So the first examples were given by Bogomolov-Chinkel. These examples have very interesting also properties for arithmetics and hyperbolicity and so on. Now the core map. And now maybe the main result is this. For any x, there exists a unique map, which I call the core of x, and this is Cx, for example, which has the following properties. 1, its general fiber is special, and 2, we have its orbifold base is of general type. And so this means that you can split completely canonically. This is functorial. This is functorial in the following sense. Yes, this is functorial in the following sense. If you have a surjective map here then this induces also a map between the cores here. So you have this is factorial, and so this gives a splitting of any x between special fibers and general type. And you should think that general type is the exact opposite of special. So you should see really the special manifolds of natural higher dimensional extensions of rational or elliptic curves. And so we have this kind of result. I have forgotten maybe to mention, yes. Yeah, okay. So we have this, this is the core map, and so this is quite important. So the extreme cases are the following one. First, you have when Cx has the same dimension of x, so this means this is the identity map, and this corresponds to the fact that x is of general type. The other thing is when Cx is 1 point, then you have just, this means that x is special. Yes, and so, yes, so some corollaries of this is the following. If x prime to x, maybe this is u, is finite, unramified. So this is an unramified cover of x, for example, then I take, there is a more general statement, then x special implies x prime special. Yes, I should mention one easy thing. If you have a surjective map from x prime to x, if x prime is special, then x is special. This is very easy. The image of something special is special. But here, for the x special implies x prime special, usually the statements about étale covers are completely trivial. But this is surprisingly difficult, and I'm not able to show this without using the uniqueness of this map here. And so let me explain why this is true. Essentially, this is just, I can assume that x prime is Galois of group G over x. So x is just the quotient. You can make a further base change to make this Galois. And so if this is Galois, this means now that by the uniqueness, we have the map here which goes to Cx prime, and here we have the map going to Cx, which is here 1 point. And we want to show that Cx prime is 1 point also. So assume that this is not true, so that this is of positive dimension. So what happens when, corresponding to this, we have Bogomolov sheaf which injects in some omega p. This is of dimension p inside of omega p of x prime. Omega p of x prime, and this thing is invariant under the Galois action by the uniqueness. And because of the uniqueness, this means that this sheaf will descend on x to a sheaf of rank 1, also inside of omega p of x. But this contradicts the fact that x was special. So you have to use all these results and the core map and its uniqueness. And so this is very surprising for me that this is so difficult to prove this. Maybe I missed something simple, but I don't believe, because you see we came to this because of certain properties here, and I think that the étale property is not so obvious. And a corollary too, which is the following: if say that variety, irreducible variety, is special, if so is its desingularization. Take a smooth model, and you say that V is special if so are all of its smooth models. Corollary 2, when we have X is special, if only if it is covered, there is a chain connected covering of X by special subvarieties. So the meaning is that you can connect any 2 points of X by a chain of special subvarieties. So this is very, very similar to rationally connected, except that you take special things. One has to be cautious that it is possible that there is no covering family of special subvarieties in strict special subvarieties in an X special. Take, for example, X. This is a simple abelian variety. Then all of its subvarieties of positive dimension, except X itself, are of general type, and so you don't have this kind of chain. So this let's do something, and also something. I stop like this. I don't. I think because of time, I have to speak a little bit more. Stop here. And now, yes. And now I will go to the unpleasant thing. This is the decomposition. Let me call this just C. See, this is just a symbol which represents the core map for any X here. And so decomposition C, this is G of R power N of the core map. So this will mimic the decomposition we took in the former times, where we were assuming the main conjecture about that uniruled means kappa is minus infinity. So here we shall take a different conjecture, and we will get some similar decomposition, but now not using this. Essentially, this will be the orbital version of the previous decomposition. And this orbital version, so this means that in fact, we see this a little bit here. If we, what are the, yes, sometimes people say, yes, the manifolds with kappa is, yes, a Fano, say. The Fano, or kappa is 0, or general type, these are building blocks for the construction of all manifolds. But here, what we see is something which is slightly different, is that in general, the building blocks are not manifolds with these properties, but these are orbifold with these properties. And so this is what we shall do here. So here we assume, in the next, assume that CNM orb conjecture holds. Then what we have, what we saw is that we had two maps. This was X to Rx, say. And we had also the map G, the Murchison vibration, which was going from R to G of R. For example, if kappa of R was greater than or equal to 0. Kappa greater than to 0. And so we saw that we could compose these two maps always for any X. Here, assuming the main conjecture, we could do this. And now we will mimic this in the orbifold situation. And now the trouble is that we don't know exactly what are, I have a definition, but in the orbifold situation, what are the rationally connected objects. And so we shall start with a very simple definition. It is possible to do better, but I will just keep with the simplest thing. So what we let me give a first definition. Kappa plus of x, this is minus infinity. If we have, if kappa of z is minus infinity for any f from f going onto z rational. So let me give this definition here in this. And so what we have seen in the talk yesterday was that if the main conjecture is true, kappa plus of x is minus infinity, this is equivalent to x is rationally connected. So we have seen yesterday. And now we shall mimic this, but with orbifold things. So the definition will be the following, that kappa plus of x d, so I take a smooth orbifold here, is minus infinity if kappa of z, and here I have to take kz plus d and f d here. The thing which I didn't define but very quickly here in this case is minus infinity for any f, say d to z. And so you have to take neat models in order to define this. And this is independent from the neat models. And so we have this. And this is, let me say that this is a weak version of rational connectedness for orbifolds. And now the point is this. And now we have the point is this. We have, or maybe the proposition, because we make a very strong assumption. Assume then it is possible to show that for any xd, there exists a unique vibration, I call it xd to r and dr, which has the following property, such that one, kappa neat, say, neat by making modifications. I have to explain what is a birational equivalence here, but I don't do this. If one kappa of r dr is greater than or equal to 0, and 2, we have kappa plus of x, I call it r, and here k kappa plus, yes, of d restricted to x r, this is minus infinity, where x r, this is the general fiber of r. So we have this. If we assume this property, so this means that we can decompose any orbifolds this in such a way. So this is the exact analog of a rational quotient map or MRC vibration, but for orbifold in this situation. So you have such a map, and here you have this positivity property, and here we have this property. And so this means that now, exactly in this, we are in the situation as yesterday. I skipped many technical details here because it's not possible to. So we have this property, and so the consequence, this implies that now I will now notice that for any xd now with kappa of xd is greater than or equal to 0, there exists also again Itaka Moishizan fibration, which goes from xd to some g of xd, and here we have where the kappa of x j, so this is the generic fiber, and d restricted to xj, this is equal to 0. So we have unique fibration. No, there is a unique, and this is the one given. This is given by phi m of kx plus d. So this is the fibration exactly as in the usual case, but we replace here just kx by kx plus d, and so we have this fibration. So this is easy. In the difficult part is this. This is exactly the same thing, and so we can now conclude for any xd. We have first we have xd goes to rd, maybe dr. So this is the map R, and so we have next the second rdr, which goes. Let me call it x1 d1 as yesterday, and so this is the map. So you can always compose this map, and so if the composition of these two maps is the identity, you have, so this means that xd is the same of the x1 d1, then this means exactly that xd was of general type. And so we can conclude exactly as yesterday that now with the conclusion, so we have this map, and the theorem is the following. The theorem is assume C and M orb. Then we have the core map, which is defined. I take x0, which is x. I just simplify in this case, but although we have no orbital structure here, but they will arrive immediately. You will see. So we have an C, this is G or power N. So this means that we can decompose it, the map C, which is the core map that we have defined before. This is the orbital, we can get the orbital decomposition. But let me really show you that in this case, we really need the orbital thing. Example. Take our example where we had our surface X, which was going to P1, actually to P1, and with this delta, which was the sum of 1 minus 1 over 2 of these points, Pi here. So we got this, and so we see that here we have this decomposition, and this is J, so this is J, and this is also J R, and this is also J R squared. In fact, if you think a little bit, this is exactly the same, because I start is here, when I apply R, I get just X, so nothing is changed, so this is the same thing, and now it will, because this is of an orbital dimension 1 of a general type, when you apply J and R and so on, this doesn't move. This is already the thing. And so this is just the simplest example of something where you have this kind of decomposition. And do you see, in general, for surface, by taking étal covers, you may always avoid this. But in dimension 3 and higher, you can't. So you need really to work with this kind of objects. And so, yes, maybe I will state some conjectures. This decomposition, so this means, I should have said it. So in particular, assume that we start with something which is special, but X is special. So what does it mean? This means that the core map, this attributes to a point. And so this means exactly that X is a tower of vibrations of orbitals with either kappa plus is minus infinity or kappa is 0. So this is a tower of such things. And the higher the dimension, the longer the tower can be. So the tower can be of length 2 times n at most. But this happens in, there are examples for any possible length and dimensions and so on. So you have this. And I would like to mention quickly that once you have this motivate the kind of conjecture, this conjecture, because we expect that these orbitals here, they behave exactly like rationally connected manifolds. And these things with kappa is 0, but they also behave exactly like manifolds with C1 is 0. And we can state conjectures without orbifold, but which are inspired by this. So the conjecture is this. 2 conjectures, 3 conjectures about special manifolds. First, X is special implies that pi 1 of X is almost a billion. Almost a billion. So X special stable by deformation, plus specialization. Specialization, and 3, maybe more interesting. X is special, should be equivalent to, first, this is the Kobayashi pseudometric, I don't define it, but equivalent to the following thing: there should exist some H C to X holomorphic, this is holomorphic with Zariski dance image. And here a stronger version should be, of course, these are all of these are conjectures, and this equivalent to for any X, Y are connected by entire curves. An entire curve, this is the image of such a holomorphic map. So do you see? So in some sense, being special should be equivalent to have to be, in some sense, rationally connected, but you replace algebraic maps from P1 by, or algebraic maps from C by transcendental maps to C. The thing just that this is true, for example, this is the obvious case, but for abelian varieties, certainly. You can connect 2 points, of course, by such things. So this is one thing. And now on the arithmetic side, I'm finished here, arithmetic side. And so we have 4. Assume that X is defined over K, which is a number field. Let me give a definition. That X, this is the definition of people working in arithmetic geometry, is potentially dense. Potentially dense if X of K prime is Zariski dense. For some K prime, this is a finite extension. So in other words, if you have something which is defined over a number field, so embedded in some projective space by equations with coefficients in K, so if you enlarge a little bit the field of definition, then you should be able to find a Zariski dense subset of a rational point. And so this is just a definition. And so the conjecture is that X over K, as before, and this is special if and only if this is potentially dense. Potentially dense, I abbreviate it by this. If and only if potentially dense. So there are
Is conjecture?
This is, no, yes, this is a conjecture. Let me think that, say that this is already open for K-free surfaces. So no problem to, in general, for general K-free surfaces, this is not known. So, but if you want, the point is that this decomposition, this strongly suggests this, but you have also to extend the definition of what are the entire curves, holomorphic curves, when you have some D here, and what are the thing xd you want to say what are the rational points or the integral points, and I will give an idea of, in the next talk of what it is. And this is just for the special manifolds. And now for general manifolds, there are also corresponding conjectures corresponding to the fact that we have a map to the core, and that the core map is, we have something which is of general type, and which prevents both algebraic entire maps through the general point, and should also, after longs, for example, this should also prevent having many rational points. So I will speak of this in the next talk. So, sorry, thank you.
Second known.
Pardon?
About last conjecture. Second known.
What?
Last conjecture.
Last conjecture. Yes, there are things which are known. For example, if you take abelian varieties, then this is known, but this is easy. There are very easy cases, even in K-free surface case, for example, if you have an infinite automorphism group, or if you have some very special elliptic fibrations with some salient multi-sections, then you have something. But the point is that one is only able to deal with abelian, the abelian case. If you are not inside an abelian or things, then you don't know.
So, no evidence.
No, but a very interesting case. This is the case of quartics, for example. Even for Fano, this is not known. The arithmetic conjecture is not known for Fano. Free false.